All right, so in this particular lesson, we're going to look at probably one of the odder applications of Newton's second law, and that's when we talk about uniform circular motion. And so uniform circular motion is anytime an object is moving in a circle at a constant speed. Now, I know my little circle here doesn't look like it's moving at a constant speed. That's actually an optical illusion, by the way. If any of you can figure out why that's an optical illusion, has to do with the line above the circle and the line below the circle when it was moving, that you have no frame of reference as it's moving up and down, but you do have something to refer to when it's moving side to side. If you look really closely at the circle, you will notice that it is moving at a constant speed. So, this is the case where speed is constant, but remember that velocity is changing, that speed and velocity do not have the same definition. And so this object is accelerating because of its change in direction. And we can actually define that acceleration as v squared over r. Now you might ask yourself, and I hope that you're asking yourself, why v squared over r? Where does that come from? Well, come in on a day and ask me to do the derivation for you. There is a derivation of why this is v squared over r. I can actually do two different derivations and prove that's true. One of them is a straight up trigonometry derivation, and the second one is actually a calculus-based derivation. Both of them you can get this expression v squared over r to pop out as the acceleration of an object that moves in a circle. And those are just two derivations that I know. I'm willing to bet that there's probably a few more out there if you really wanted to dig into that. Well, if the acceleration that we would call centripetal acceleration is v squared over r, it's also worth pointing out that acceleration is always toward the center of the circle. The way this motion is always changing as the object is moving closer to the center of the circle. Well, not necessarily closer, but toward the center of the circle. That's the way velocity is changing. So the net force must be ma, or mv squared over r. And again, that force acts toward the center of the circle. So we're going to do a couple of example problems and show how we can use this to actually figure out some things about a system. And so here we have a problem dealing with a modern race car, and modern race cars are designed to produce something that's called negative lift. And what negative lift is, it's a force that pushes a race car downward as it travels. Now the reason for this force is that if you have an additional force that pushes the race car downward as well as gravity, you increase the normal force acting on the race car, and you also increase both the static frictional force and the kinetic frictional force. And so you actually increase, more importantly, the maximum static frictional force, so you can increase the maximum speed at which a car can turn a corner. If you've ever seen on the back of like a sports car or in a race car, usually what we call a spoiler or a fin, basically what those are designed to do is produce negative lift and allows you to turn corners faster. So we want to calculate the amount of negative lift that would be needed for a race car that is 600 kilograms and is going to complete a circular turn that has a radius of 100 meters at 30 meters per second. It's going to be a flat racetrack, and the coefficient of friction between the road and the tires is 0.75. So if we look at the forces that act on the object, here we have V. And the one thing to point out is that the frictional force is acting toward the center of the circle. It's actually static friction that allows this race car to go around the corner. The reason for that is, or the reason why it's not kinetic friction, is if you look really closely at where the tire contacts the surface of the road, you see that point-to-point contact, that the surface of the tire is not sliding along the surface of the road. The tire is rolling along the road, so each point of contact stays stationary for an instant on the road. So let's do a quick free body diagram, and I'm going to say to the left is toward the center of the circle. And so we actually have four forces. Three of them are ones you probably would have already guessed: the weight due to gravity, the normal force, and the frictional force. The last one is this FL, and this FL is that negative lift force that we want to calculate out. So one thing that we have to say is that, well, frictional force has to be equal to the centripetal force. What's causing the object to go in the circle is the frictional force. Friction is accelerating this object in a circle. So whatever the frictional force is, that has to be equal to mv squared over r. One thing that I can say about the forces up and down is that the normal force has to be equal to the weight and the negative lift force added together. Another thing that I can say about the frictional force is the maximum frictional force has to be equal to mu s times Fn. Now, it's worth pointing out that this maximum frictional force would relate to the minimum FL. There's nothing I can do to change Fg, so to make Fn smaller, FL must be smaller. So we can actually solve this out for Fn, which then I could substitute in over here after I've solved for FL. So add FL, mv squared over mu s times r minus Fg, and we get, if you plug all those numbers in, we get 1,320 newtons is the smallest value of negative lift that allows this situation to be true. Now, it's worth pointing out, any value of negative lift that's bigger than 1,320 newtons would allow this car to move around this corner. So the second problem that I have a roller coaster that's going to move in a vertical circular loop that has a radius of 15 meters as it goes up and down. And I want to know, what is the minimum speed that the roller coaster needs at the top of the loop? And you might say, well, that's pretty obvious. We could use conservation of energy and say, well, it could be at a speed of 0 at the top of the loop. Well, if it's at its highest location, speed of 0 makes sense. But the one thing to point out is, if the speed is 0, what happened to this car if it got to the top of the loop and stopped is the car would fall straight down. So it must have some speed in order to continue moving through the loop as it's moving in this circle. So let's try to calculate what that minimum speed is. Now, there are two forces acting on the car at the top. One is the normal force and one is the weight. And it happens to work out that the centripetal force, mv squared over r, is actually equal to both the weight and the normal force. So one thing that we could do is we could rearrange this a little bit. Now, I can't really change how big your weight is, but I could, in this situation, change how big the normal force is. Your weight is a fixed value, but the normal force might be altered, and really your normal force is going to depend upon how big V is. If V is the smallest it can possibly be, the normal force must be 0. Now, this is actually kind of an interesting situation here, because if you've ever ridden on a roller coaster through a loop or ridden on any carnival ride that goes through a vertical circle, you know that in some parts of the circle you feel heavier, and in other parts of the circle you feel lighter. You may have also experienced this on an airplane, like when an airplane takes off, you feel heavier for an instant. Or when an airplane lands or starts to descend, you might feel lighter at certain points in time at that descent. And it's really a similar type of factor here, that your perception of how heavy or light you are is really the normal force acting on you, not the force due to gravity. In fact, when we talk about something being in free fall or being weightless, we really mean the force, there's no normal force acting on it. You don't experience that force due to gravity. So let's plug that in. Mg is equal to mv squared over r, and we can actually solve this without needing the mass of the car or the people. It doesn't matter how many people are on there, which is actually pretty convenient if you're a roller coaster designer. You don't need to change the speed of the roller coaster for the number of people that's on it. You can imagine if you did need to do that, having everybody stand on a scale and calculate out how much the weight of those people is. That'd be kind of a pain. So if we actually solve this out, we get the minimum speed is 12.1 meters per second at the top of the loop. If you're going any faster or any slower at the top of the loop, your car is going to fall off the circle. If you're going faster, well, you can go faster. You're just going to experience more normal force. The last problem that I have deals with a scenario like this. And I've picked this scenario for a very specific reason. This is what's called a cloverleaf interchange. It's shown on the right. It's a very common type of road feature found on Minnesota highways. You can actually find some of these coming into town here in Faribault. This type of interchange involves some sort of circular exit ramp that connects one lane of traffic to another lane of traffic. This would be what we would call a full cloverleaf. There are 4 cloverleafs. You can have a half cloverleaf, which is kind of like one of the exits here in Faribault. You can have even like a quarter cloverleaf, which is kind of like another exit that we have here in Faribault. The reason why I picked this one is that during Minnesota winters, this type of design can pose a serious design challenge. And the serious design challenge is that icy conditions can sometimes lead to the coefficient of static friction being essentially zero. Now, this is not a problem if you're traveling down a straight highway, because you don't need to turn left and right. As long as you don't turn the wheel of your car, you're perfectly fine. The problem is, when you need to go through a tight circle, you need to be able to get through this circle. The solution to this problem is to do what we call bank the exit ramp. Make the outside of that corner higher than the inside of that corner. And so we want to make it possible to travel in an exit ramp with a 30-meter radius at 10 meters per second under the worst possible conditions we can ever think of. So coefficient of friction of 0 is the worst possible ice you could ever have on the road. So you're talking about like a bald tire, no tread or grip on the tire, ice with grease and oil on top of the ice, worst possible scenario that you can ever think of. So we want to figure out what is the angle that I should bank the ramp at. So here I have the outside of the corner, the inside of the corner. The two forces that I really have acting in this object is the weight and the normal force. If there's no frictional force, there's no other forces acting on the object. The centripetal force should be acting toward the center of the corner. And so really, the x direction I'm going to make in this case horizontal in the direction of the centripetal force, and the y direction in the direction of weight. Now this is also an instance where normal force and weight are not the same. So if we look at the only other force that acts in the x direction is a component of the normal force, and it's got to be Fn sine theta. Because this is theta, which means that that angle has to be theta, similar right triangles, which means that this side has to be opposite. If you look at the y components, the y component of normal force and the y component of weight, and the weight, have to be the same. So we can actually solve this out. Fn cosine of theta equals mg. We can solve it for Fn. Substitute it in. We can divide both sides by m. Remember that sine over cosine is tangent. And there we go. We have an equation that relates g, v, and r to one another. It's worth pointing out that there's no mass in this equation. Again, it doesn't matter whether you're driving the smallest passenger car or the biggest semi-truck you can think of. Same corner, same speed. So if we actually try to solve this for theta, probably easiest to divide both sides by g and then do inverse tangent. You find that 18.8 degrees is the angle that you should bank this at. The one thing to point out about this situation that's different from the frictional force situation, the race car, in the race car problem, you could travel any speed less than 30 meters per second or of any force larger than that value and still get around that corner. In this case, this is the angle that you have to have. And 10 meters per second is the speed you must have. If one of those things is wrong, well, you're going to either end up on this side, falling into this ramp, or sliding off the ramp this way. There's a second reason why I've picked this particular problem, and it deals with a personal experience that I've had dealing with this type of exit ramp in icy conditions. And this deals with driving to my parents' house on Thanksgiving one time. My daughter is sitting in the car seat in the back of the car. My brother is sitting in the passenger seat, and Mrs. Inman is sitting right behind me behind the driver's seat. And we start to make a corner, and I lose control of the vehicle going around in the corner. I happen to have been going at the exact right speed to make it around that corner in that particular situation, or in that particular scenario. Given the bank of the corner, the radius of the curve, all of those things, by some stroke of luck, I was going that exact special speed that my car was able to do, actually more than a complete 360, because we ended up facing backwards and end up at the bottom of the exit ramp, where all I had to do was turn around and keep going. So when it says that the exit ramp is 35 meters or 35 miles per hour, that's why it's 35 miles an hour. That's the situation they're looking at or dealing with. Second, it deals with some uniform circular problems. The one thing to point out is really it's an application of Newton's second law in looking at forces.